What's up guys, this is Jahangir from Medporium, and today we're going to be talking about acids and bases in terms of organic chemistry. So to start off with that, we really need to talk about or sort of review our acids and bases and the definitions. So let's start with the Bronsted-Lowry definition. First, let's talk about the Bronsted-Lowry acids, and these are proton donors, because when we're talking about the Bronsted-Lowry definition, we're really talking about those hydrogens, so those H pluses, and a proton donor is going to be our Bronsted-Lowry acid. So what that pretty much looks like is if we had HCl, and we'll say that this was mixed in with, some water, and this HCl the chlorine will pretty much release that hydrogen, and this results in a negatively charged chlorine and a hydrogen. And this is an acid because this component, this HCl, hydrochloric acid, released a hydrogen, which makes it an acid, and this is actually one of the strongest acids out there. Now let's talk about the Bronsted-Lowry base, and this is pretty much the opposite of the acid. So in the acid we had proton donor, so the opposite of that would be our proton acceptor. So an example of this is if we had hydrogen and we had this Cn minus, and this creates HCN, and this would be a base. This would be a Bronsted-Lowry base because it has accepted the hydrogen from that solution or whatever we're looking at. Now let's talk about the Lewis definition of our acids and bases, and this really includes electrons. So in our Lewis acid-base definition, we're really talking about electrons. Now what makes a Lewis acid is that this is an electron acceptor. And what makes a Lewis base is the exact opposite, so that would be electron donor. Now, to identify your Lewis acids and Lewis bases, your bases are usually going to be electron rich. So they might even have a negative charge as well. So negative charge, which implies that we are electron rich. Now, with Lewis acids, we're usually going to have like a positive charge, but if you don't have that, you're always going to see at least one of those molecules have a negative charge or some lone pairs, which indicates that that's a Lewis base. So now that we know both the definition of the Bronsted-Lowry acid base and the Lewis acid base, we're going to use those to form our organic chemistry definition of acids and bases. So our organic acid definition is going to bring in that Bronsted-Lowry definition of acids, in which we're going to have a hydrogen, like a positively charged hydrogen. We might also have a H3O plus hydronium or a protonated alcohol, which alcohol is going to be that OH, so a protonated version of that would just be that H. Now for our base, this is going to pull in from the Lewis base definition, in which we're going to have an atom that has lone pairs, pretty much electron rich like we were talking about, and something that will bind to H+. So this definition of our organic base really leans into that Lewis base, and this definition of acid really leans into the Bronsted-Lowry definition of acids. So you can see that there's a mix of both of those two definitions, and that's how we build our definition for our organic chemistry, what we're going to go through all of these problems. All right, so let's go through this problem, and let's first ask ourselves which one is going to be our acid and which one is going to be our base. So when we were talking about the definition of those acids and bases, we really want to look at our reactant side and see the effects on the product side. So let's start with this organic molecule to the left, this first one over here. So when we go from the reactants to the products, we're losing a hydrogen. Now when we lose a hydrogen, we're pretty much adding hydrogen to the solution, which makes this an acid according to our Bronsted-Lowry definition of acid, as well as our organic definition of our acid. Now this hydroxide over here will turn to H2O, and we have a negative charge, and we also have lone pairs on that oxygen. So this is pretty electron rich, and this is what's going to form our base. Now that we know that, we need to identify our conjugate base and conjugate acid. Now, if you have an acid on the reactant side, then you are going to end up with a conjugate base, and vice versa. If you have a base on the reactant side, this is going to turn into a conjugate acid. So let's look at this one here, and I want you to pause the video and see if you can identify which one is the acid and base. Now automatically, if you know your strong acids and even strong bases, over here our HCl is our strong acid. So this is just going to be an acid, and since this is an acid, we're going to have our MgOH as our base over here. And another backup or another reasoning that this is an acid is because we go from HCl to just chlorine by itself, so it lost that hydrogen, while over here with that magnesium, we're losing that hydroxide. And if you lose a hydroxide, then you pretty much are a base, because hydroxide is like the antithesis of a hydrogen. If you add hydroxide to a solution, you're making it more basic. If you add hydrogen to a solution, you're making it more acidic. Now, there are definitely going to be some questions that are going to ask you which one is the Lewis acid and the Lewis base. So it's something like, let's say we had boron and then we had 3 fluorines over here. And over here, let's just say we have a nitrogen and H3. So the question might ask us, which one is the Lewis acid and which one is going to be our Lewis base. So if we remember our definition of Lewis acid to start off with, Lewis acid are going to be those electron acceptors. So it's going to be anything that has maybe a positive charge or maybe no lone pairs, because they're not electron rich. They're electron deficient. While our Lewis base is going to have those lone pairs. Forgot to put these lone pairs on the nitrogen over here. But you can see clearly that nitrogen has those 2 lone pairs. They are electron rich. So what happens is this nitrogen over here is going to be our Lewis base, and it is, we could say, attack the boron over here, and it pretty much pulls that boron to form this molecule right here. Now boron is going to have a minus charge because we're bringing 3 electrons in, but we have 4 electrons around, so 3 minus 4 is going to be -1. And for this nitrogen over here, nitrogen has 5 electrons and there's only 4, so 5 minus 4 is going to be that 1. So we're overall going to have a neutral charge, but we're going to have a formal charge on that nitrogen and that boron. Now let's say you had carbon dioxide and water. So I want you to pause this video and identify which one is your Lewis base and which one is your Lewis acid. So Lewis base is going to be our H2O over here, because this is electron rich. We have those lone pairs over here, which pretty much are going to that carbon right here, and this is going to form this sort of molecule right here. So we're going to have a minus charge over here, minus formal charge, and we're going to have a +1 formal charge for this oxygen, and this is what we end up with. So over here, and I'm just going to label this real quickly. Water is going to be our Lewis base, and carbon dioxide is going to be our Lewis acid because it's accepting electrons. Lewis base, this water is donating those electrons. So now let's talk about pKa and what that actually means. So pKa, and already here, pKa is going to equal our negative log of our Ka. Ka was our acid dissociation constant, and Ka basically tells you how strong an acid is. So if you have a high Ka, that means you have a really strong acid. Now, this is going to be an inverse relationship with our pKa, because if we have a larger, so we have a larger and I'll write more positive pKa, then I'll write pKa over here. If we have a larger, more positive pKa, then this is going to indicate a weak acid. So this is basically saying if you have a more negative and smaller pKa, then you're going to have a stronger acid. So it's basically saying, like, if you have a pKa of 35 compared to -2, this -2 pKa is going to indicate a very strong acid compared to this 35 pKa, or whatever molecule that is. And talking about strengths of acid, another thing to note is that our acidity will increase with the stabilization of our conjugate base. So when our conjugate base is created and that is more stable, which we'll see in more of our problems and just illustrate that, that will really show how strong that acid is if we have a more stable conjugate base. So let's say we had this organic molecule over here, which has a thiol group or sulfohydryl group, which is actually one of the most important functional groups to know. And we have this hydrogen over here. So to start off with, we need to know which one is our acid and which one is our base. Now, as we talked about with our organic definition, our base is going to be electron rich, and it might even have a negative charge and a lone pair, which is exactly what this hydrogen has. So by doing some arrow pushing, we can push that towards this hydrogen over here. So the hydrogen to the right is going to pull the hydrogen from this thiol group, creating H2, or we're just going to show it as H bonded to H, so hydrogen bonded to hydrogen. Just as reference, we're going to write this as our base. Reason why is because this is electron rich, has a negative charge, and lone pairs just indicating that it is electron rich. And over here is our thiol group, so this is accepting the electron from that hydrogen, making it a acid. So now that we know that this acid, this thiol group, is not going to have that hydrogen anymore. So what's going to look like is we still have our carbons and we have that sulfur right there. And when we put our lone pairs, the sulfur is going to have that formal negative charge, and this is going to result in our conjugate base. And over here is our conjugate acid. Now, more than likely during an exam, you're going to be given a table showing you all the pKa's for a bunch of different molecules. But over here, you're going to have this thiol group that's going to have a pKa of about 10. And we can look at our conjugate acid over here, and this is going to have a pKa of 35. So when you look at pKa table, you obviously have to look for these acids because pKa is going to be that negative log for the acid dissociation constant. So as you can see, we're going from this lower pKa to a higher pKa, meaning we're going from a strong acid, a stronger acid, to a weaker acid. And that's exactly what we want. And this reaction is going to be product favored. So product favored. And the reaction is going to move from reactants to products, meaning that this is going to result in a complete reaction. So this is exactly what we want. We want to make sure that we start off with a low pKa, and when we move to the products, we have a higher pKa. So this is going from strong acid to weak acid, which is exactly what we want for all of our reactions in order to understand if the acid-base reaction actually occurs from left to right. So now let's look at this question right here. So first off, we have an alcohol group over here, and we have our carbonyl. And we first need to identify, as usual, which one's going to be our acid, which one's going to be our base. So I want you to pause this video and identify which one is your acid, which one is your base. And if you want to as well, show some arrow pushing to show where those electrons are going. So over here, this oxygen over here is going to be, this molecule entirely is going to be our base because this oxygen has a negative formal charge and we have lone pairs indicating that it's electron rich. So either one of these electrons we can move for arrow pushing, doesn't really matter. I'll just move this one over here to that hydrogen, and this oxygen will pull that hydrogen, or pretty much attacking that hydrogen, ripping apart the hydrogen from its group over here. So in the reactant side, what we're going to see is the alcohol on this carbon that has that carbonyl group over here, and we have this organic molecule over here that is going to have a negative formal charge because that oxygen's hydrogen was ripped apart. So this, for reference, is our base, this is our acid, and then over here, since this was our base, this is going to be our conjugate acid. And over here, since this was our acid, this is going to be our conjugate base. So if we look at the pKa table, we're going to see that this molecule over here has a pKa of about 16, and over here, our acid over here is going to have a pKa of 4.7. Now, one thing you'll notice is that on the reactant side, we have a higher pKa than the product side. So we have 16. 16 is a lot greater than 4.7. And this means that we are going from a weak acid to a strong acid. And since we're doing that, our reactants are going to be favored. So we have reactants favored. This is the opposite from our last question where we had our products favored because we're going from strong to weak. But now we're going from weak to strong. So that means this reaction is going to be completed going from right to left. So now let's talk about our pKa's and how it relates to different organic molecules. Meaning if we add like a couple molecules here, maybe like a carbon, like more carbons, or we add electronegative atoms in there, how would that change our pKa? Meaning how would that increase or decrease our acidity of our organic molecules? So I'm going to illustrate a bunch of different organic molecules and label some random pKa's, and we're going to match them to each of those molecules. All right, so here's our molecules and here are our pKa's. So let's go down each one of these and see which one is a stronger acid. So over here we have a carbonyl group, we have an alcohol, or actually we have a carboxyl group over here. So we're just gonna look at that, and it doesn't have anything special. It's just carbon, hydrogen, oxygen. So that's just one thing to keep in the back of our mind. Now over here, we have a chlorine over here, and in our third molecule, we have fluorine. So here's how electronegativity really affects acidity. So if you remember from our past videos, electronegativity is this idea that there's atoms that really want to hog electrons. Like they're very selfish and they want to pull the electron density, or you could say the attention, towards them. So when they do that, and let's look at this chlorine over here, for example. This chlorine is, you could think of it as someone that really requires a lot of attention. Like a baby, for example. A baby needs a lot of attention. Maybe they're crying for food, or they're crying to change their diaper, anything like that. They need a lot of attention, and maybe there's this sibling over here, like the oldest sibling, you can think of it as hydrogen, and these oxygens are the parents over here. So this chlorine over here is pretty much a crying baby, and these parents over here will give more attention to the baby, let's say it's a newborn baby, instead of the sibling over here who might be in high school. So they're not going to give a lot of attention, and you could think of it as the molecules where we can release this hydrogen much easily, and that makes it a stronger acid, because stronger acids dissociate much more easily. Now, if we look at this fluorine over here, we could think of it as 3 newborn babies. And these parents over here are going to give a lot of attention to those babies to the point where this high school student is going to be neglected. So they won't have a lot of attention. Maybe they had some activities with mom and dad, which aren't happening anymore because there's 3 newborns that have to be taken care of. And that's what makes it a stronger acid, is when you have these electronegative atoms, they're going to hog the electron density. They're going to take all the attention away from these 2 oxygens or whatever other molecules there are. And this hydrogen won't get enough love, so it'll just be released. So automatically, fluorine is more electronegative than chlorine, because if you look at the periodic table, fluorine is above chlorine, so that makes it much more electronegative because it has a smaller atomic radius. So fluorine over here is going to have the lowest pKa. And chlorine over here, since this molecule over here doesn't have any electronegative atoms, this is going to have the second lowest pKa. So this is going to be second strongest acid. Now we get into these 2 molecules over here, and it does become a debate. But that's only until you understand that over here we have a methyl group. So we're going to have a CH3 right here, where in this molecule our CH3 is somewhere over here. So we have a C2 over here and we have a CH3. So we're going to have more carbons. And what happens is, this is called the donating electron density effect, or we could just say donating electron density. And what happens is, this electron density from the carbon is basically donated to these oxygens over here because they become the most electronegative, and this actually makes the acid a little bit more weaker. So this is going to have the lowest pKa. This is going to be, or the highest pKa. This one is going to have the third highest pKa. You could think about those carbons, since those electronegative atoms, we were saying they're like babies, like newborn babies. We could think of this CH3 or anything like that as like daycare for those babies, or maybe a babysitter or a nanny or something like that, in which that electron density or the attention will go back into this sibling over here, this high school student who wasn't seen enough from their parents. They didn't have that attention. So now these oxygens can give attention back to that hydrogen, and this creates a weaker acid because they don't want to release that hydrogen as easily as this molecule right here, which we don't have that extra carbon. So now let's go through just a couple more examples of our acid-base reactions, and more importantly, arrow pushing. That's one topic that can get a little confusing for some people. So let's say we have hydrofluoric acid in this molecule over here, and always with these acid-base reactions, before we do any arrow pushing or anything, you have to identify which one is your acid and which one is your base. So looking at our base definition, we know that if we have lone pairs, that indicates electron rich. If we have a negative charge, that indicates electron rich. We have lone pairs on this molecule right here. So what's going to happen is these two electrons are going to be donated to this hydrogen. This hydrogen is going to accept them. So this is our base over here. This is going to be our acid. So this hydrogen is going to accept those electrons. And what happens is this molecule over here is basically going to pull that hydrogen towards itself. And this results in a fluorine that's pretty much all alone by itself, taking that negative charge. Because if you look at formal charge, fluorine brings 7 electrons in. There's 8. 7 minus 8, -1. So we're going to have our H, C, and then 3 bonds. And this is what we end up with as our molecule. And nitrogen over here has a +1 charge. Now you might be wondering on the reactant side, well, how did that fluorine get those 2 electrons? Well, what happens is when that nitrogen takes away this hydrogen, that bond will be broken. And there's 2 electrons in this one bond, so these electrons will go back to that fluorine, and that's why we see those 2 electrons. With arrow pushing, we're basically pushing these electrons away and showing that it's moving from one side to another. Either this bond over here turns into electrons, or these electrons turn into a bond. So hopefully you now understand what pKa is, how that relates to acid-base reactions, and also how to look at those different organic molecules and see which one is a stronger and weaker acid. And as always, a Pomodoro day will make you a doctor someday. I'll see you guys in the next one.